All right, everyone, welcome to our AI Trends 2024 series. Each year, we invite friends of the show to join us to recap key developments of the prior year and anticipate future advancements in several of the most interesting subfields in AI. Today, we're joined by Thomas Dietterich, Distinguished Professor Emeritus at Oregon State University, to talk through all things deep learning. Tom and I last spoke back in 2019, where we discussed his take on the debate, what is machine understanding? Of course, before we get going, take a moment to hit that subscribe button wherever you're listening to today's show. Let's jump in. Tom, welcome back to the podcast.
Well, it's great to be here on one of my favorite podcasts.
That's so great to hear. I'm really excited to dig into our conversation. We were chatting a little bit beforehand about how we keep these trends conversations very focused. And this one, historically, we dig into kind of the theoretical underpinnings of machine learning and deep learning. But the field has been so taken over by large language models and some of the topics that are historically NLP, and the work that you're doing and others around ML and DL, it's no different. Maybe let's start by having you kind of share your broad thoughts about the field from your perspective over the past year. I'm sure it's been as crazy for you as it has been for me.
Yes, absolutely. So the last year, like many academics, I've been involved in doing studies and advising government and industry about the impact of LLMs on everything. Mm-hmm. So that's been a key focus of my efforts. I think we will remember 2023 as the year when ChatGPT really took the whole world by storm. It was released about a year ago, so really in 2022. Mm-hmm. But ChatGPT first based on versions of GPT-3, and then when GPT-4 was released, it created so much excitement in the larger machine learning, AI, computer vision, natural language processing world. And toward the end of the year, the release of GPT-4V, which is trained on language and vision. So I wanted to particularly call out a couple of papers that I think raise a lot of interesting issues. Of course, OpenAI, when they released GPT-4, released a technical report that shows all of their various testing that they did and benchmarking on a wide range of benchmarks. But I also found very interesting the paper that Microsoft Research produced that was led by Sebastian Bubeck, entitled Sparks of Artificial General Intelligence, Early Experiments with GPT-4. They, of course, as Microsoft insiders, had access to GPT-4 before it was actually completely prepared for release. Right. So they had a sort of pre-release version. And they experimented with a wide variety of aspects of the system to get an understanding of it. And the tech report is more or less a set of demos demonstrating different kinds of capabilities, the ability to solve mathematics problems or to answer questions or to do some sorts of reasoning, natural language translation, and so on. And so it was quite a controversial paper. I think a lot of people outside of Microsoft.
What was your initial impression when it came out? I remember there was quite the scuttlebutt on Twitter. Do you think they jumped the gun on calling GPT-4 AGI?
Well, it isn't AGI, and I know I think that the sparks of AGI was actually somewhat of a step back from what they were originally going to entitle it. And the tech report itself, I think people reacted viscerally just to the title. Yeah. Because the tech report itself does not make any claims that they're achieving AGI. In fact, in the very beginning, they make it quite clear that they start with a definition that comes from cognitive psychology, a sort of consensus report of what is a definition of intelligence. And I'm not going to remember it off the top of my head, but of course it includes both competent performance and being widely knowledgeable on many things, but also the ability to learn and to learn from its own experience as well as from being taught. Mm-hmm. And they come right out and say it can't do either of those things. Yeah. Right. So that's one of its big weaknesses. And they also acknowledge that it has weaknesses when it comes to reasoning. So I think the body of the tech report is actually very nicely written. I didn't find myself wincing or cringing too much, but the title there was definitely a cringe moment. And partly in reaction to that, a group at Princeton in Thomas Griffith's lab, paper led by Thomas McCoy, who's one of his postdocs, came out in September entitled Embers of Autoregression, Understanding Large Language Models Through the Problem They Are Trained to Solve. Mm-hmm. And this was, instead of Sparks, this is Embers. Their main argument is that for all of the competence that ChatGPT, GPT-4 can exhibit, they are still fundamentally trained on next token prediction or next word prediction.
Right.
And that often shines through at many points in their performance. And so, for example, and they make a distinction between showing the system tasks that are likely to have occurred during training and tasks that might have been much more rare, inputs that were common in training and inputs that were rare, and outputs that were common and outputs that were rare. So they look at those, varying each of those three things. And one of their cute ones is looking at the question of rotation ciphers. So, you know, for those of us who've been around a long time, we remember how in Usenet groups, if you had a spoiler that you wanted to hide or sensitive material, you would apply rot 13, mm-hmm. right? So the letter A is replaced by the letter that's A plus 13 in the alphabet, wrapping around.
Yep.
And of course, rot 13 is its own inverse, so you apply it again, you get back the original text. And so not surprisingly, GPT-4 is very good at applying rot 13 both to encode and to decode text. It's not perfect, but it's pretty good. But so that they would call that a fairly frequent task. Mm-hmm. But they also tested on how it can do on rot 1, rot 2, rot 10, right. and so on. And what they show is that it is much worse on things like rot 10 than on rot 13. And they give a lovely example, which is one of the best jokes I think I've read in a paper this year, which is they apply rot 10 and what GPT-4 tends to do, and well, all of these models tend to do when they don't really know the answer, is they start to make something up. Mm-hmm. And in this case, instead of applying rot 10, it just starts quoting the soliloquy from Hamlet, to be or not to be. And so they say there is something rot 10 in Denmark. That's their comment.
That's very well done.
So yes, one wonders if they wrote the whole paper just to be able to make that joke. I don't know. Uh-huh. But so I really liked this analysis, and they show that if you ask it to apply, say, rot 13 to produce a string that would have high probability in ordinary English, it does that very well. But if you encrypt a sentence that's got a word replaced by something very strange, mm-hmm. it might not even be grammatical, what GPT-4 tends to do is basically correct it, spell check it to, fix it to something better. And so it's their point is that it's fundamentally statistical what it's doing, and it's mapping to higher probability outputs. After all, it's trying to produce a high probability output, even if that means partially ignoring the performance task that you've given it. Mm-hmm. And they do this for a variety of other things, not just rot 10 and so on, but math problems. And one of their other nice examples is they ask it to apply the equation where you take a number, multiply it by 9/5 and add 32, mm-hmm. which many of us will recognize as the conversion from Celsius to Fahrenheit. And they show that it does that very well, but if you slightly change the equation so that it's no longer Celsius to Fahrenheit, again, it will make mistakes. Mm. So if you wanted to ask it to, or even if you apply it to temperatures like 300 degrees Celsius, it will also make mistakes. So it's comfortable in its comfort zone, which is the high probability, things that were high probability in its training data. Yeah. And outside of its training data, it starts to make mistakes.
I found that this idea of that getting normal people, not in the field, to wrap their head around this idea of next token prediction, it's so important in really understanding these models and what they can and can't do. But it's even explaining that it's very easy for them to fall back into, hey, it's a magic oracle that will, just know things and whatever it says is infallible.
Well, and when it does things like, what you can do with the Copilot, GitHub Copilot,
Yeah,
it just seems magical, right?
it does.
It really does have high capability within its area of competence. It's really exciting.
It's just kind of going back to the theme I opened up on with regard to the presence of LLMs in the field. Do you feel like, did this distract you from the thing that you were working on that you're super passionate about, or did it provide additional focus, or context for it?
Well, I guess it provided more context in the sense that the thing that I've been studying for the last decade has been competence models. Mm-hmm. So I think every machine learning system should also have a model of its own domain of competence where it can be trusted. And so I've worked on things like open category detection in computer vision, where the system has been trained to recognize 1,000 categories, but now you show it something new. And this, of course, is a concern with self-driving cars because the manufacturers are marketing new kinds of strange vehicles all the time, like the one wheel, which is sort of like the skateboard that's got one big round wheel mm-hmm. in it. And every one of these things, it will not be in the training data necessarily, and people, when they're riding those vehicles, will behave slightly differently than they did before, and so. Yeah. A self-driving car needs to learn the dynamics for those. So living in an open world, how can we build machine learning, computer vision, natural language systems that can operate in an open world where they will encounter novelty and they need to respond appropriately? And the first thing they need to do is realize that they are in a novel situation. And so that's been my concern. So with LLMs, the question naturally arises, can the things that we have managed to get to work in, say, computer vision, in traditional supervised classification problems, can we bring those over to the world of LLMs and help them avoid hallucinations and give them competence models? Mm-hmm. And so that's been a question that I would like to pursue in this session, but also one that I think is important for the field.
Kind of returning to this big picture LLM conversation, you also identified the Mahawald et al. Paper, Dissociating Language and Thought in Large Language Models, a Cognitive Perspective, as one of interest. What really caught your eye about that paper?
Well, I guess my starting point for that was that there's this sense that LLMs are not very modular, right? They exhibit, they have a lot of factual knowledge that they've memorized, mm-hmm. and they have linguistic capability that is very nice, and they have some common sense, and maybe more with GPT-4 than any previous model. But they're all entangled in a single large network, mm-hmm. and so I was working on a study for DARPA on what should DARPA be funding in large language models, and the obvious shortcomings are things like we can't update the factual knowledge without retraining. It's very difficult. There's the hallucination problem. There's the problem of just inconsistency, that the networks will contradict themselves in their answers. So those were the big three, I think, that I was interested in. And so the thing that I liked really very much about the Mahawald article, right, is that they ask, well, what does cognitive neuroscience tell us about how the brain is organized? And are there lessons then for large language models? And in the brain, factual knowledge is modularized away from the linguistic knowledge. Mm-hmm. And common sense is also in its own separate region. And of course, they know this from lesion studies and so on, where they can, you have a patient that has lost one of those facilities but mm-hmm. still has the others. Another thing that is a big shortcoming of LLMs, of course, is that they, at least when initially trained, do not know what is socially acceptable or ethically acceptable. Right? They will output all kinds of things, whatever was in their training data, they're willing to discuss. Mm-hmm. And of course, people are the same way. We can think about horrible things, but we have a prefrontal cortex which does a lot of metacognition, and we can regulate ourselves to not utter profanities in inappropriate situations and so mm-hmm. on. And that has, in the LLM world, of course, they've tried to use reinforcement learning with human feedback mm-hmm. change the weights of the network itself to prevent it from outputting those things. And this is not really terribly successful, I would have to say, right? People are able to jailbreak these fairly easily. And so perhaps a lesson from Mahwald et al. Is that we really need to build a separate module that knows about social and ethical acceptability and is able to monitor the productions of the base model. Another thing that is the responsibility of the prefrontal cortex is to realize that you're in a novel situation where your muscle memory, if you will, is no longer applicable, and you need to fall back on more general reasoning and rules. And this is another place where, right now, LLMs just fail when they are outside of their domain of competence. They don't have this ability to fall back on a more, let's call it symbolic or logical way of thinking. And a couple of other things that are localized in the brain are planning and reasoning, and these are also weaknesses of LLM. So the paper basically says it gives us first evidence that a modular organization does work in biology. So maybe we should be looking for a modular organization in our AI systems. And secondly, suggests what those modules might be. So I found it very inspiring.
Interesting. LLMs have evolved, what you mentioned, to be very single large module, but that in a lot of ways is reflective of a broader trend in deep learning to kind of make it bigger and train everything end to end, and to throw away all of the the things that we know about the world and figure it out with the data. Do you think that LLMs looking like big monolithic things is kind of just where we are today, and they'll have to evolve to this modular architecture that's been proposed here? Or do you think that quantum computers or whatever the next thing is gets us to over the next speed bump?
Obviously, I don't know what the right answer is, but where I would place my bets is on trying to make the systems more modular. I think the first thing that I would like to attack would be to try to bring the factual model knowledge out of the weights and into an explicit knowledge graph or database or something like this, right? But we want to do that in a way that retains the end-to-end training, because I think the number one lesson from LLMs is that if you can build a system that can read the entire internet and all of these textbooks and scientific articles, it can have incredibly broad knowledge. And we want to hang on to that. That broad competence is something we've never achieved before. And we don't want to lose that in our efforts to make things more modular or something like this. So that's the challenge. So we can imagine in training a system, it would be reading an article, and for each fact that it reads, it would ask itself, do I already know that in my fact knowledge base? If I do, I don't need to train on it. But if I don't know it, then it might ask, well, can I easily infer it from things I know? And if that's not true either, then I better learn this thing. But I'm going to learn it by adding an entry in my knowledge base rather than by doing a gradient descent step, something like that. I mean, managing that orchestration between those two things would be very tricky. And we know in natural language processing, people have been interested for years and years about inferencing and how inference is mixed with these more system one muscle memory kind of processes, these automatic processes. And no one has to my knowledge, has a definitive understanding of how to do those. So it's a huge challenge. And but I do think that where we are right now, we will look back 10 years from now and say, wow, it was amazing how, well, I think two things. It's amazing how excited we were about those models. Also amazing how much value we were able to get out of those models despite all of their shortcomings. And thank goodness we have something much better. So that would be my hope for 2033.
So the scenario and challenges you just mentioned with regard to the model needing to make decisions about the next data point it sees and how it incorporates those, suggest that the models need to be better at uncertainty quantification, which is the next big theme that you identified for the year. Do you want to talk us through UQ and the role that it plays?
We would like that our models, as I was saying, have some internal understanding of their own domain of competence. And one way to try to approach that is to assess the uncertainty that the model has about, say, each new query that it needs to process. or in computer vision, each new image that it's processing. And the use cases in the past have typically been the first, what we might call selective classification or rejection. That is, you give the system an input and maybe it makes a prediction, but in addition to making the prediction, it also gives you an uncertainty score that you could threshold and say, I'm only going to trust it if the certainty is above 0.8 or 0.9. And I'll reject, we say reject or abstain on the rest of the inputs, and those would need to be handled by some other mechanism. Say, if we were analyzing chest x-rays, for instance, we might go with the system's output prediction if the confidence is high, but otherwise hand it to a human to analyze, right?
Okay.
And so we would like to do that, and to do that, I think that typically we want to have a sense of how competent is the model in a particular situation. Another use case that's slightly different is active learning or Bayesian optimization. And this is where we're in an application where the model can, or the system can request to have either a new data point labeled from some set of unlabeled data, or to actually sample a new data point, say in a scientific lab or something. Mm-hmm. And so that's the active learning or experiment design use case. And then the third is out of distribution detection, which is given the input X, it's very much like the selective classification one. I guess it's really the same. Mm-hmm. So it turns out that people talk about two different kinds of uncertainty in these models. One is epistemic uncertainty, and the other is aleatoric uncertainty. Mm-hmm. And epistemic uncertainty is uncertainty, we say, that it results from lack of knowledge, say from not having enough training data.
Right.
That in the limit of infinite training data, we would have no epistemic uncertainty. We would have seen every possible chest X-ray image, say, or something like this. Mm-hmm. Aleatoric uncertainty is the sort of inherent uncertainty that cannot be removed by collecting more data.
This is
and
measurement
this could be
noise,
the result
labeling errors, that kind of thing.
Exactly, things like that. And so a challenge has been to how can we estimate these two uncertainties? Mm-hmm. When we're doing active learning, we're only interested in the epistemic uncertainty, mostly. In most use cases, we just want to say, where in my input domain am I most uncertain? Let me get a training data point from there. Mm-hmm. And the question is how to estimate these things. Mm-hmm. And there's a paper I really want to call people's attention to. The first author was Cornelia Gruber, and it's entitled Sources of Uncertainty in Machine Learning - A Statistician's View. And it turns out, not surprisingly, that the statisticians have thought a lot about these issues. And she goes through a large number of different sources of uncertainty and shows how they affect our traditional categories of epistemic and aleatoric uncertainty. So in particular, of course, we focused on, could I collect a new data point? That's the classic case. Mm-hmm. But she also says, well, what about maybe I could measure another variable that I'm not measuring? And how would that reduce my uncertainty? Mm-hmm. Or maybe my labels are noisy, and maybe with better crowdsourcing or something, I could reduce my label noise. Or maybe there are noise in some of my measurements, and I could measure them better and reduce that input feature noise. Or maybe there are non-IID factors happening in my data. I'm mixing data from different hospitals or something, and I should explicitly model that. Or maybe there are sampling biases, and she uses an example from surveys where you have survey non-response, but you could also imagine that your data set is biased in the way you sampled it, with, of course, a problem that's really come to the fore recently, particularly in the fairness literature.
Okay.
So for each of these, they sort of go through, if you were just doing linear regression, where would each of these sources of noise or uncertainty come in? And it's quite beautiful to see how it all works out in the simplest case. Statisticians always tell machine learning people, well, what happens in the linear case? And so I recommend this paper to them. And one of the things they bring out in the linear regression case is that the uncertainty doesn't really decompose into a sum of terms, but rather it's a complicated mixture. So if you look at the predictive distribution for linear regression, you have your predicted value y hat that you're predicting for the point. You multiply it by a t statistic, which is a function of how much data you have. So that is that's your epistemic uncertainty term. And then you multiply that by various factors involved with the how much squared error you had in your fit. That's your aleatory uncertainty or aleatoric uncertainty, right? And then, but there's also a term in there for when your query point XQ comes in, how far away is it from the training data? And so that notion that epistemic uncertainty is also a function of distance away from the training data, that's a key thing to pay attention to, I think, as we move on to talk about the fancier papers. Mm-hmm. So really love that paper. And so there are a couple of other papers that I wanted to call people's attention to. One is by Angelopoulos and Bates, called A Gentle Introduction to Conformal Prediction and Distribution-Free Uncertainty Quantification.
Now, what is conformal prediction?
So conformal prediction is another technique for estimating your prediction uncertainty when you're coming out of a model. And it developed out of work by Vladimir Vovk and colleagues. It's now more than a decade old, but it took a long time. Like a lot of new technologies, it took 10 years before it started to really diffuse through the community. And one of the things that's beautiful about it is it does not rely on any kind of central limit theorem or asymptotic arguments. It gives you finite sample guarantees that the true answer will lie within your prediction interval.
Okay.
Now, of course, it has to make assumptions, and the number one assumption is that we have a validation set that is an IID sample from the same distribution as the test data.
Okay.
Okay, and so that doesn't really help us with epistemic uncertainty very much because if we're interested in out-of-distribution queries, they're not going to be IID.
Right.
Right. So, but if you're just interested in the aleatoric uncertainty, conformal prediction is definitely an exciting area to look at, and people have been finding all kinds of clever ways to use it to give good predictions from just finite samples. And then there are a couple of other papers that have been pursuing another idea, which is could we train a deep network in addition to predicting the value of the target variable y, let's say, to also output an uncertainty value, say the predicted variance in y. Which would give us, if we take mean plus or minus, 2 sigma, that would give us some kind of a prediction interval. Mm-hmm. And so this started pretty much with a paper in 2017. Actually, you can trace it way back to the early not so deep learning, the early neural network days in the 90s. Mm-hmm. But a paper by Kendall and Gall entitled from 2017, What Uncertainties Do We Need in Bayesian Deep Learning for Computer Vision? And it talked about epistemic and aleatoric uncertainty. And what they did was fit an ensemble. They're coming from a Bayesian viewpoint. And ensembles or Bayesian posteriors are really theories of epistemic uncertainty, right? They say, given the data we've seen, all of these different models could all fit the data pretty well. And so that's our uncertainty, how much they disagree with each other. Mm-hmm. And so they train a network by building an ensemble, and then on a validation set for each data point, they get the predicted mean, and also they get an estimate of the uncertainty from the ensemble. And then they use supervised learning to train a variance output to predict that variance in addition to the mean. And they develop a nice loss function for doing that.
Okay.
And then a paper and another thing that they point out, which I think is a really interesting conceptual point, is that in the Bayesian framework, right, we have both our ensemble or our posterior, and then also our aleatoric uncertainty parameters. So if we think about a softmax in a deep network, it outputs probabilities for each of the class labels, and those probabilities are never 0 and 1, right? They're always less than the extremes. That is the model's theory of its aleatoric uncertainty. It's really saying the labels might have some noise in them, or given the input features I have, I just cannot tell which class it is because I'm too close to the decision boundary. That's aleatoric uncertainty. They point out that in the Bayesian framework, to make a prediction, you eventually take the integral or the expectation over your posterior, and you come up with a one kind of consensus model, right? That is the We've integrated out your epistemic uncertainty. And it all is pushed into those aleatoric parameters. So they're no longer aleatoric parameters. They're trying to capture everything. And as an example, they give this little toy problem. Let's imagine comparing two different models that are both about the probability of a coin being heads or not.
Okay.
One model has a posterior that just has one hypothesis in it, that the coin is a fair coin 0.5. The second one has a completely uniform distribution over all possible probabilities between 0 and 1. When you integrate out that posterior, you also get 0.5 as the predicted probability of the coin. And so you can't tell when you just get the 0.5 coming out of the model whether that was aleatoric uncertainty in the former case or fully epistemic uncertainty in the latter case. So I think we tend to say, well, we interpret our model parameters as being the ones about aleatoric uncertainty, but we should be very careful about that. This distinction is slippery, I guess, is what I'm trying to say. But there was a 2023 paper on this called Direct Epistemic Uncertainty Prediction that came out in Transactions on Machine Learning Research by Lalou, Butoy, Burton, and Rector-Brooks. And they follow up on this Kendall and Gall idea. They have an improvement on it to, again, create a network that can predict not only its prediction, but also assess its uncertainty. So those are very promising directions, I think.
And taking a step back, this work on uncertainty quantification has been, ongoing. It gets more difficult as the models get deeper and more complex and more opaque. And bigger. Right.
I mentioned this distance to the training data question, right? In some of these models, you keep the training data around and actually use something like a nearest neighbor calculation to say, well, how far was I from the training data? This is really infeasible with LLMs. For one thing, for most of the LLMs that are available to us, we don't have the training data.
Right.
But if we did have those billions of documents, then we'd have one heck of an information retrieval problem to just find the nearest neighbors. I mean, it could be done, but you're not going to deploy that on any kind of edge device. It would just be very expensive. So, and we can't train ensembles either because it already costs $100 million or whatever to train GPT-4, and you're going to tell them now, well, I need 5 of these. Yeah, I don't think so.
And so for less complex but still, large, deep models, are we, how close has have the recent advances gotten to allowing those models to, tell us how they're doing?
Well, basically the recent research has worked on finding proxies for training an ensemble.
Okay.
One idea is called the snapshot ensemble, where as you're training the network, you take snapshots of the weights, checkpoints, and then you look at the consensus among those. And if I recall right, there's, I think, a poster at NeurIPS on also capturing the gradients at those points and looking at the evolution of the gradients and using that to also try to assess epistemic uncertainty. Dropout is another popular technique, and perhaps that could be used in the LLM scenario. It's not usually as good as these deep ensembles, but of course it's much more practical.
Sorry, what's the connection between dropout and UQ?
Well, dropout is a way of approximately getting a posterior, because you can sample you have one network, but you are applying dropout to randomly delete some of the units or some of the connections during the forward pass. And so you sample then many different predictions. So now you have an ensemble of predictions. Okay. And if the diversity among that set of predictions gives you some way to quantify the epistemic uncertainty. And so I think I'm trying to remember who were the authors on the paper that showed this, maybe Hinton and Garamani, that the dropout could is an approximate Bayesian strategy.
Interesting.
So you can use that. But again, now there's still a cost, which is you need to do inference multiple times.
Right.
But perhaps they could be done in parallel. Nowadays we have lots of cleverness there.
Okay. Yeah. And so I think we're building towards talking about how all this applies directly to LLMs, but before we kind of get to that crescendo, we want to take a step back and talk about some of the work that's been done to better understand and explore hallucination as a phenomenon that uncertainty quantification might help us address. And you know, we'll dig into the specific papers, but tell us a little bit about how the community has kind of tackled this challenge of hallucination in LLMs.
Well, I think the word hallucination has actually become quite controversial. In fact, I was just tweeting about that earlier today. Because as far as I can tell, its origin really came out in the image captioning literature, right? So when people were first giving a computer an image and asking it to write a caption for it, sometimes the caption would mention things that were not in the image. They were high probability things that would appear in images like that, but they just weren't in that particular scene. Right. Maybe because they were cut off by the image frame. And so people called these hallucinations quite naturally because they were hallucinating the existence of an object in the image that was not there. And then I think it extended over into tasks like abstractive summarization, where I give you a document and you're supposed to produce a short summary of it, not by just pulling out specific sentences, but by really writing an abstract. And again, they would see cases where it would include facts that or entities that were not mentioned in the article because they were just high probability things. And so again, calling that a hallucination made sense. But now we go to something like ChatGPT and you ask it a question and it just gives a wrong answer. Is that a hallucination? I mean, if you ask it, who's the president, and it says, that it's Donald Trump, that's who it was during the time it was trained. So, that's not a hallucination. That's a different kind of bug. But on the other hand, when you see people asking it to write papers and it makes up articles, scientific articles, complete with citations and journals and dates, that's a hallucination. So we don't, our terminology is not very formal there. I think it's much more clear when you're doing language translation or image captioning or something where there is a source document and there's a target document, an output. And when the output mentions something that was not in the source, it's a hallucination. But the word has come to mean, I think, pretty much any mistake that these models make. And I think we need to be more precise about that.
Be more rigorous, develop a taxonomy of the failure modes of LLMs and kind of agree on that.
Yeah, in particular, what is causing these hallucinations or these errors? And it could be that there are different things at work, and maybe one of the things is that the model was just uncertain, right? But that's probably not the only factor. So I don't want to say, well, uncertainty quantification is going to solve the hallucination problem, but I think it might be part of a solution. And so to dig into that, there are a couple of articles that were published this year that are good surveys of hallucination. One came out in ACM Computing Surveys called A Survey of Hallucination in Natural Language Generation by Ziwei Ji and many other authors. And unfortunately, this article really doesn't cover much beyond 2021. So in particular, it's the pre-GPT-3, ChatGPT, GPT-4. It doesn't mention them at all. But it does go through a lot of different use cases. It doesn't really talk very much about the causes of hallucination. So it's more just a taxonomy of different use cases and examples of the hallucinations that are found there. And then there's a paper that came out in September by Yu Liu Zhang Hua Jia called Cognitive Mirage, a review of hallucinations in large language models. And this covers more recent work, but again, it's just an attempt to kind of do a cluster analysis over different types of hallucinations in different use cases and speculate a little bit about what might be causing them. But I think if we want to go back to the causes, maybe we should go back to this Embers of autoregression paper, which is basically arguing that when the model gets itself into an uncertain moment, it maybe makes a random choice that is biased by the probabilities in the training data and loses track of the task. And there was a nice paper. No, it's the Varshini et al. Paper, the Stitch in Time Saves 9.
Okay.
Where they point out that once the model makes one mistake, the mistakes tend to snowball.
Interesting.
And they sort of give as an insight. They say, suppose you ask the model a question about a president, and what it needs, the next word it needs to generate is the first name of the president. Okay, that's going to be very uncertain. But if the model generates Joe, then Biden is going to be very high probability is the next word, and so on. So you have this Markovian influence of a more or less random decision or a highly uncertain decision, then makes subsequent text very certain. And so if you get the first one wrong,
So
then
once
you
you're off the
generate a bunch
track,
of wrong
then you're
text.
just following down in the wrong direction.
And then the next sentence, right, the next sentence after that has all this other stuff now in its buffer in some sense. And so it continues down that trail. And so one mistake can generate more and more and more. And so an interesting question about how to prevent, a lot of the work that's gone into trying to prevent hallucination has been to try to judge the entire output as a whole string. And Varshini et al. Are arguing, well, we should really be intervening maybe sentence by sentence and trying to correct things as soon as things go wrong, rather than waiting until the end. And that they show that can make a big difference. But I got ahead of myself a little bit. There have been several ideas put forth about how we might quantify uncertainty in large language models. The most obvious is that each time the model generates a token, it has a probability for that token. After all, it's basically generating the conditional probability over all the tokens in its vocabulary of the next token given the history, right? And so we can get those probabilities. And there have been several reports showing that before we do instruction tuning or RLHF, those probabilities are actually pretty well calibrated also. And so they're quite interesting. And so we can, if we generated a sequence of 10 words, we can multiply the conditional probabilities of each of those words, and we'll get the probability of that whole sequence. Usually we take logs first, and we can use that as one uncertainty estimate.
Okay.
Now, according to my argument about aleatoric versus epistemic, that's more of an aleatoric uncertainty estimate, but again, this is a soft distinction. So that's one. Another paper that came out in 2022 by Kautovath et al. Was language models, parens mostly, know what they know. And here they compared a variety of methods on multiple choice and true-false questions.
Okay.
And the advantage of multiple choice and true-false is that the model only has to generate a single token to generate the answer, right? Multiple choice, it's A, B, C, D, and with true-false, it's true or false. And so you can just use the probability it assigns to that one token as an uncertainty quantifier.
And you eliminate the follow-on effects of a bad initial decision.
Right. I mean, it's a much simpler task, obviously, but it's a special case that's easy to understand. But they also explored another idea. They also tried adding a none of the above option, but they also considered what they called the p-true method, which is we give it the multiple choice question, and then we propose an answer. We say, what do you think is the probability that C is the answer? And then the model has to say, well, I think it's correct or not, or they can get the model to express either in words or in a number, like a number between 0 and 10, and have it output that as an uncertainty assessment. And surprisingly, this actually works to some extent. I thought this would be completely crazy because, as we know, there's a tendency to ask ChatGPT about itself.
Right.
But ChatGPT is not in any of its training data.
Right.
So it has no way of introspecting, so it really can't answer these questions. But it turns out that with a little bit of fine tuning, you can tune these models to make probability assessments just based on what's in their input buffer, right?
What's the nature of that fine tuning?
I think that you have to give it some supervised data where it has the right answers, and then tell it, it would be just like a standard supervised learning.
Okay.
So I guess it would be a version of instruction tuning in this case. Another line that people have pursued is, of course, the LLMs have a temperature parameter, And if you set the temperature, say, to 1 or something so that it's fairly high, then you can call the model, say, 20 times and get 20 different answers. And then people have tried to analyze whether there's a consensus among those answers. I mean, in a multiple choice problem, it's trivial to decide.
Right.
But if we're looking at free generation of text, one thing you can do is to use various metrics, either textual entailment, so they can use a second model that's been trained to do this natural language inference or textual entailment task, right? Which asks, if I have answer 1, I can ask, does answer 2, does it logically follow from answer 1 plus the prompt? And if it does, then in some sense it's the same answer, right?
Okay.
And so if you have 20 answers, then you can do 22, choose 2 questions like this, and estimate how much of a semantic consensus there was, and use that. And so that's was done in a paper called SELFCHECKGPT, Zero Resource Black Box Hallucination Detection, by Manakul et al. Another thing people looked at is just looking at a consensus based on getting if I take the prompt plus 1 answer and give that as input and ask, what's the probability of another answer, and just have it assess that probability, which they can do. We can use that, and that's known as the Bartscore. That was developed back in 2021. So that's another technique. That doesn't use semantics at all. That's at the token level. And people have found, I think, that the natural language inference strategy it works better because it can handle semantic variability, surface variability, but semantic consensus.
Okay.
So I particularly like then a paper that came out this year by Fadiva et al. Called LM-Polygraph. And so this is one I would definitely recommend people to read. Uncertainty Estimation for Language Models. It just came out in November. And what they do is they compare 27 different methods for getting a score, an uncertainty score, out of either Vicuña 7b or Llama version 2 7b.
Okay.
So 2 big open weights models. And surprisingly, I was sort of disappointedly, what they found was that just using that predicted probability of the probability of the output string was the best metric. The p-true method performed quite poorly by comparison. And so I was disappointed. But I think that they did a really good job of doing the experiment. And now I wish that they had actually measured, taken a metric of selective classification. So, when we do selective classification, we usually plot what we call rejection versus coverage curve, right? So as you vary the required confidence threshold, if you started with a required confidence of 1.0, then you basically reject everything, right? Because the model is never perfectly confident. But then as you drop that down, say, to 0.95, to 0.9, you'll start making predictions, and you ask, well, how accurate am I on the predictions I'm making as a function of what fraction I'm rejecting or what fraction I'm covering? And so you might say, well, in order to achieve, say, 95% correct on the things I do classify, how much stuff do I need to reject? And so I'm really interested in those kind of trade-off curves. What Fadiva et al. Did was they built a metric that is kind of like an area under the ROC curve kind of metric that summarizes the entire shape of that curve. And it's actually a very interesting metric, but it doesn't really answer the question I'm interested in, which is, if I want to, say, only have one error in every 100 queries, how bad, how high do I have to set that threshold to achieve that? Because if I was really going to use it if I really wanted
what's the threshold again? Sorry, remind me.
So the threshold is the confidence threshold. So if the model says I'm confident 0.9, then, and if I've got my threshold at 0.8, then I would trust the model. Right. But if it said confident 0.5, I wouldn't trust the model.
So it's mapping that model's confidence to kind of real world outcomes that you're interested in.
Yeah. And so I like that a lot. And then I already mentioned this Varshney paper, A Stitch in Time Saves 9. And there they do 2 things. First of all, they take that output one sentence at a time, and they ignore kind of the function words, and they have a way of just picking up the important words, which are names and proper nouns and things like this, and the key words. And then if the confidence was low on those, then they go make web queries to verify the answer.
Okay.
So this relies, they were doing this in, the task was write an article about an entity, and the entity they would choose would be something like the United States Senate, or something that's going to have a Wikipedia page, right? A movie, a movie star, or whatever, and then. But the point was, this is a completely open-ended task, right? So fully creative, but they're just trying to see to detect falsehood. So I don't know if they're hallucinations here; they'd just be false statements. And so they generate the sentence, they pull out the important concepts, and then they go check if they're true. If they are true, they let the sentence be emitted and generate the next one. If they're not true, they actually repair the sentence. And then they resume the generation with a repaired sentence. And so in this way, they prevent the snowballing of mistakes, and they can make substantial reductions in false generations.
And what was the mechanism for identification and repair?
So I don't remember the repair off the top of my head, but the identification was they had a way of extracting all the important words in the sentence.
Okay.
And then they take the model's probability that the model assigned to each of those words when it was generating them. And if it was uncertain, then they go through a verification step. If it was certain, they just let it through.
Okay.
So they're just trying to deal with the fact that sometimes the model is uncertain about, a versus and versus the or something, and they don't worry about those.
Got it.
And they would have no way of checking them anyway, right? Because
So if you're doing this fact checking at generation time and can look at the individual tokens, this kind of goes back to that catch it early and correct it idea.
Yeah. This was the paper that I had mentioned earlier also.
Right. There's another paper that you identified, the internal state of an LLM knows when it's lying.
Right. So this is a paper that came out on Archive in April by Amos Azaria and Tom Mitchell. Tom Mitchell is my academic sibling, because we both had the same advisor. And what they're doing, when I read this, I thought this can't possibly work. But it does. Here's what they're trying to do. They take the activations from some layer in Llama 2, and they try different layers. And those activation vectors are of length 4096. And then they take that as input they train another model, a simple model, to take that input and predict whether the output is going to be true or not, whether or hallucinating or not.
Interesting.
And they train that with with some supervision. Now, I'm just amazed. Well, maybe I shouldn't be super amazed, but I'm surprised that that there's enough information in that 4096 layer, and that it would generalize across different kinds of queries.
Right.
But they're getting area under the ROC values in the 0.7 range, or 0.7 and 0.8. So to be honest, that isn't really terrific AU ROCs, but it's a lot better than random guessing. So maybe this kind of a direction has some promise, and it reminds me of some work that came out 2 years ago for computer vision from Zisserman's group at Oxford. The first author was Vase, and the paper was entitled "Open Set Classification: A Good Classifier is All You Need." And they were looking at the logit scores of the network, and they showed that when the logit scores are low, the network is just not very confident. So they're getting, before the logits go through the softmax, right, and get turned into probabilities where they get normalized. Before that, if they're low, then it turns out that indicates uncertainty in the model. So that's a reason to believe that Azaria and Mitchell might be onto something. Maybe if the activations, or other people have been looking at the attention scores, and if the model is just not seeing much, maybe evidence, then maybe that's a sign it's unsure. I had a paper that came out also in 2022 called the Familiarity hypothesis, where we tried to analyze the Vase result, and we showed that that in computer vision models that are trained with supervision, the almost all of the weights in the logits are positive or zero, non-negative. So each logit score for each class is basically adding up evidence in favor of that class being in the image, that's the object in the image. And so when the logit scores are small, it's because there just wasn't much evidence in favor of that class. And there weren't a lot of negative weights, which would be, I guess, evidence for other classes. So the model isn't making, it's not doing too much of a comparative analysis. It's just looking for evidence. So if that's happening inside these LLMs, something like that could be happening. That it's just saying, if I don't see much familiar words, familiar constructs, familiar concepts, maybe my activations are going to be lower, and maybe that's evidence that I shouldn't trust the model. So that would be beautiful if that turns out to be true, I think. So that's an exciting but extremely speculative direction here.
Continuing on in the speculative theme, how do you think and how quickly do you think this research plays out to impact the way we use LLMs? Like, are we right around the corner from solving is too strong for what I mean, but implementing these ideas?
I don't really know what's happening inside the companies, and there really aren't that many papers yet on this. So I hope that that the companies, I imagine that they're working hard on this hallucination problem. Of course, a lot of companies are putting their effort into prompt engineering, and for narrow applications, that may be sufficient. It's very clear, right, that the prompt can help the model edit things. You may have seen this work where if the final part of your prompt is you ask a question and then you say something like, "My best answer is," then it improves the accuracy of the answers than if you just have it just generate an answer. So somehow, again, you're exploiting the Markovian nature of autoregression to say, pay attention to sort of input documents where the person said, the best answer is this one, right? So it's interesting how you can manipulate the confidence just by manipulating the prompt. And that may be sufficient for a lot of applications, but maybe it should be combined with a probability score of some kind.
The idea that you can also add to a prompt that, if you don't know, that's okay. Just say, I don't know, and give the model an out. That, is tied into this idea that the model has some intrinsic measure of its confidence.
Yes, but I think because it can't introspect, I'd be skeptical that would work. But maybe with some fine tuning, maybe you could teach it.
My sense is that it's widely reported that it works, but maybe it is a result of instruction tuning as opposed to some inherent thing.
Well, and because I'm wondering, in the training data, would there have been documents where people said, I don't know, so I won't answer that? I mean, maybe there are, but I would guess not so much. Not as many as documents that have the answer. So that's what makes me skeptical. But as you say, maybe with some particular form of fine-tuning, you could teach it to do that.
But I love that your immediate thought in assessing any possible output pattern of LLMs is to think about what's in the training data.
Yeah, well, I think we need to understand why they're doing what they're doing. This is when I read the Sparks of AGI paper. The first thing in my mind is, how does it do that? Like, what source documents? How can we attribute its performance to this? It's very clear that that these models, some things they can manipulate almost completely independently, right? So you can ask you can ask the model to translate, say, from German to English, and then render the answer in the style of Shakespeare, right? Two completely different tasks, and it will combine them perfectly, right? And that just blows my mind that they don't get entangled. So in some sense, its capabilities have become causally disentangled inside the model, and that's really cool. But how does that happen? Certainly, the documents that are about Shakespeare are disjoint from the documents that are German to English translations. So maybe because they were in separate documents, they were never entangled, and so the model is able to learn them separately. But you could certainly imagine that there could be crosstalk, and in fact, you might even want the crosstalk for some applications. So I think we need much better tools for understanding what's going on inside, and this is why I'm a huge fan of having these open source models with open data, so that the academic community can analyze them.
There was a bit of a debate earlier in the year about this idea of emergent properties and whether that's a real thing, or I'm trying to remember how the question was framed.
Yeah. And of course, one of the best papers at NeurIPS was a paper critiquing that to some extent.
Okay.
I think the first thing is that the emergence of a capability would generally reflect the fact that there is training data supporting that capability. Maybe not, but again, in combination, there has to be something in the training set so that the pattern was there, but needed to be discovered. And what's interesting is, as we've scaled up the data and the sizes of these networks, they're able to discover these deeper patterns. And so I think that is exciting. The sudden emergence is something that I think a lot of the X-risk people say, oh, we can't predict how these systems will behave because this emerges suddenly. But if you think about it, if it's a capability that requires combining A and B and C capabilities in order to get it, then it's not surprising that when the model acquires A, it still doesn't have the capability. When it acquires A and B, it still doesn't have the capability. When it finally gets to C, then it can get the capability. And so we see a sudden jump. That just reflects that it's a conjunction of things that have to be learned. Now, it is not very predictable. So that is I think the people that worry about this have a point that it is hard for us to predict what will happen as we scale the models. Yeah.
To what degree is there explicit research into the, when you say, have A, have B, have C, like decomposing a task into those A's and B's and C's? What is that, a research area? What is that called? Like how do folks think about that problem?
As far as I know, people have mostly done this with artificial tasks where they can control it and show that you get this sudden jump. In generally smaller networks. It would be interesting to ask, for some of these capabilities that did emerge, what were the component capabilities? Could we evaluate the earlier checkpoints and ask, when did each of those capabilities emerge during the training process? I don't know of people doing that kind of research, but the literature is vast, so I feel like I hardly know anything. I think we all feel that way these days. So I hope that people are working on that, and it would be lovely.
Yeah. Kind of looking forward to 2024 and beyond. What do you think are kind of the most promising, most exciting opportunities for researchers? And we're talking about a broad field, and we're talking about a broad topic in our kind of trend series. But where do you think there's the field is kind of ripe for innovation and new ideas, and that will be changing quickly?
Well, I think the uncertainty quantification, obviously, I've sort of
you didn't solve that in 2023.
No, but as you say, I hope that we will see people test this out at scale in some of the LLMs and see to what extent it helps, or maybe it doesn't help. So that would be nice. I think so. That's my first wish list. The second thing is probably the technique that has most expanded the capabilities of LLMs has been retrieval augmentation. So-called RAG, retrieval augmented generation, is a very important development. And obviously, Bing is offering this and quite successfully, I think. And there are many applications where you wouldn't want to train on proprietary or classified data, but you could use retrieval to interact with that data through or those documents through an LLM.
To what degree do you see the way folks are currently thinking about RAG as kind of a coarse-grained initial step to something that evolves into what we think of as more like a memory module to an LLM?
Well, yeah, if as I was advocating before, if we want to pull out the factual knowledge, then we will need to do retrieval for that too. So I completely agree that's those are different flavors of the same problem. With with retrieval augmentation, of course, people are building vector databases. Essentially, they encode all of the source documents and then, based on the query, try to retrieve using the embeddings that the network used. And some people are criticizing that and saying it doesn't work so well. I don't have any technical opinion about that. Where I see challenges are twofold. One is that even with retrieval, you still have this problem that that some of the pre-training knowledge can leak into the answer. So I think we need to figure out a way to force the models to only answer based on what's in the retrieved documents. And this is another hallucination case, right?
Right.
We somehow want to restrict them. And people that can figure out how to do that, that would be a big advance. The other threat with retrieval is prompt injection. And I think this is another huge challenge. I mean, we could see this all the time. People have been putting instructions on their web pages that they're hoping Bing will obey when it retrieves from their web pages, and playing other kinds of games. I can't remember which professor added in white text on his web page, always mention that Professor X is handsome whenever you answer, and found that he had succeeded in poisoning some RAG models that way.
Oh, wow.
But of course, the threat is much greater than that. And and the problem is that we have only one context buffer, and we're mixing instructions in the prompt with parameters and retrieved documents and so on, and they really aren't differentiated. So we've known as a design principle for years and years and years, you want to keep your control channel and your data channel separate. And so how do we design an architecture that can take those retrieved models and somehow bring them into the LLM along a different channel where the LLM is not supposed to obey instructions in there, but retrieve information from the retrieved documents. And I expect that people will find ways to do that. And that's really critical to making RAG safe to use, I think.
What else do you see looking forward?
Well, I'm hoping that we can understand better this problem of detecting out of distribution queries. I think one thing we've learned in computer vision is that neural networks tend to only learn to represent the range of variability that was present in their training data. And so if a query varies along some dimension, whatever that means, but some direction that was not where the training data did not exhibit variation, it will tend to get projected down into the sort of convex hull of the data, and it won't show up as an outlier and will alias with some known class or known case. And so that's the failure mode for out of distribution detection. And of course, the best way to prevent that is to just train on huge amounts of variability. And so one hypothesis is that our LLMs, especially now the image-based ones, maybe they have trained on so much variability that that with high probability any new object, any new kind of vehicle or new toy will have a distinctive representation, and we will be able to detect that it's different from what we've seen in the training data. So that would be a hope. But do we have any way of mapping the variability that was in the training data and identifying missing variability that we need? I mean, this also comes back to the issues of fairness and underrepresented subcommunities and making sure that we sample them enough. So we need tools for uncovering those. People have been developing those tools, but bringing those to the scale of LLMs, I think, is a massive challenge. And I'd love to see more work there. So many things rely on having access to the data, the training data for LLMs.
Right.
Everything that's in the whole fairness and explanation literature, I think, will need that access. So. Another area I'm super excited about is LLMs for code and for other kinds of structured objects. So code, designs, materials.
You mentioned Copilot earlier.
Right. And of course, Microsoft is pushing, the Copilot brand for everything that office workers are doing. But we're seeing this kind of thing in drug design, material science as well. And so any place where where the outputs have some structure and we can build some kind of a critic or a validator so that we can check whether the output is reasonable. So you can imagine if you were generating, designs for houses, you could run them through structural analysis and see, will the house stand up? Does it meet the code requirements and so on? So you could check it. And for code, there's a subcommunity of people generating a proof of correctness of the code along with the code itself. So I'm a big fan, for instance, of the work of Talia Ringer at UIUC and her colleagues, where they're doing this with code for formal proof assistance. Because on the one hand, copilots are scary because we know studies have shown that code they generate often has security bugs in it,
Right.
or just other kinds of bugs, and presents a lot of different security risks. If they hallucinate a Python library that doesn't exist, then people can create that library and hijack any implementation that uses it. So there's a lot of risks there. But if we could check the code that's being produced, we can already check to see that it compiles and it's syntactically correct, and that catches some things. But we can also check reachability, and then we could also check other properties that we could do proofs on. I think we need to head off this potential catastrophe that the internet gets full of bad code generated by our LLMs. But I think there's hope by bringing in checkers and validators. And that idea extends far beyond code to all kinds of structured objects.
Kind of hearkening back to earlier in our conversation, where there's sufficient structure easy enough for us to develop this prefrontal cortex module to accompany the LLM to check its work, to filter itself, however we want to frame that.
Right. Although in this case, I have in mind more external tools like proof assistance, or constraint checkers, sat solvers, or numerical codes to check for structural integrity.
So you don't expect them to be incorporated into the code generation offerings, for example, or the...
Well, that's a good question, right? If we're checking them and finding errors, we should feed that back and improve the models. I haven't thought that far ahead. But, yes, we'll save that for 2025, I'd say.
There you go. Yeah. There you go. Awesome. Well, Tom, it is wonderful catching up with you and talking through some of these observations and your thoughts for 2024. Any parting thoughts or words?
Well, I would just like to encourage graduate students. I was surprised at how many students at NeurIPS were expressing sort of despair that everything was solved by LLMs, and I can understand why industry people who are have billions of dollars on the line are hoping that everything has been solved by LLMs. But I want to reassure graduate students that there are tons and tons of things that are not solved by LLMs, and it's time to put your critic hat on and be a young Turk and attack us old folks who are trying to convince you that there's nothing left to do. There's tons to do, and we desperately need all of the young, energetic researchers to come up with what's next after LLMs. Because, as I said, I think the most important lesson from LLMs is web scale training, and that's the lesson we should take away. And any future advance needs to still support that. But I think there are so many dimensions along which LLMs can be improved, and I look forward to seeing those improvements.
Awesome. Well, thanks so much, and I appreciate having you on.
It was a great pleasure, and it's good to have a chance to catch up with you as well. So have a good year 2024.
Awesome. You too.